All right, let's see. So, I think the last thing that we talked about was more or less building alignments and the different software that can be used to build alignments. I know I talked about muscle. Muscle is a really common one. I think it's a little basic, but you know, it works. But when we get to the command line, we do run into issues with codon alignments. Not a lot of programs can do a native alignment. As far as I'm aware, Prank's the only one. But that doesn't mean we can't do codon alignments. It's just we have to be kind of clever. Yeah, let me see if I can see what happens. If I change my mic volume, hopefully that's okay. Is that better? Let's see. Codon alignment. We can make a codon alignment happen. Even though it's not native, we can make it happen. We just have to use tools to help us out. And so, this is where I'm going to make that happen, or we're going to get tools that lets us do a codon alignment. So first off, my favorite aligner is MAFT, M-A-F-F-T. It's already built in. It's already there. We don't have to do any more than that. But we are going to use MAFT, and MAFT is one of my favorite aligners. It's just unfortunate it doesn't do a codon alignment. But again, we can make it do a codon alignment. And so, this is kind of a segue into GitHub. And we're probably not very familiar with GitHub. But GitHub is a repository for developers, right? This is where anybody who ever produces code and makes it public is probably going to host it on GitHub. And so I have a GitHub with a repository for this class. And so this page, I really am at github.com/my2vandy. Honestly, like my2vandy is a pretty common handle. You can probably find anything that I've ever said on the internet if you look for my2vandy, but whatever. So this is my GitHub. I don't have a lot of stuff here, but if I ever make code public, like if I've used code for a paper or something else, I'm going to put it on my GitHub. And it's easy to get stuff from GitHub. As I said, this is where developers put their stuff. If it's free, if it's public, this is where they're going to put it. And how we get that is to, one, go to the repository. So our repository that we're looking at is Bio435. And so I already have a handful of built-in scripts that are going to help us work with this stuff easier. So that's in Bio435. And so I have a handful of scripts in here. Some of it's for this class and some of it's not. Some of it I've just put up in here for students that need. They can just go ahead and grab it. And it doesn't matter where it's from, right? I've had kids from Philadelphia download my stuff. Doesn't matter. And so I have a little bit of a help tutorial on some of these scripts. Basically usage tutorials, right? So one of the most common ones that we'll use is translate.py. And so this is a Python script. Python's really handy for text manipulation and pulling stuff out of text files. We don't have enough time to do any Python programming, so we're not going to. So if I have to do something in Python, I'm just going to make it and then make that script available to you. But yeah, so the two scripts that we're going to use today is translate and then reverse translate. And so there are tutorials, like at least a little usage line of how to actually call this thing. So you're going to call the script name and then a input FASTA file, have your open char to save your file to a protein file of your choosing, right? Again, recognize the brackets. The carets are not literal. The only literal caret is our save caret. But I have a couple others in here that we're gonna additionally use. So if you download this stuff, definitely, like, before asking me how do I use this stuff, look at the help menu first. Anyways, so if we want to download this stuff, and this is for y'all as well, if you want to download this stuff, how you would do that, and this is true for any GitHub repository, we just go to the code and grab this HTTP link. And so it's going to be very similar to using wget, but in this case we're going to use git to download this folder. And so this is fair for y'all as well, if whenever you get around to this, to download, given this link. So I just copied that link. I just Control-C to copy that link. And so this line, if we're downloading from GitHub, is going to be git clone and then the link. And that's it. And so whatever is in this repository, whatever is in this folder online, will be downloaded to a directory called Bio435. Again, this is public if you ever want to use it. It's at your own risk, but it's fair. I don't put a lot of effort into error calling. That's kind of a theme among developers, is to at least put in some error control. No error control, because most of the time I'm doing a quick thing, it's for myself, and yeah. So now I have this new folder, Bio435. And so everything in here, almost anything in here should be green. Because it's a script, it's a Python script. And we can look at some of this stuff. I mean, it's text, so we can look at it, not necessarily because we're trying to figure out what it's doing, just so you can see that it's just code. And it is text. It's not binary or anything. It is editable, and we can look at it. All right. Now, I'm going to get rid of this because I already have this saved somewhere. So I'm just going to get rid of it nonetheless. Yeah. Okay. Because I already have this in a directory in my software bio. Right, so I already had these scripts somewhere else, so I don't want to duplicate it. I don't want to waste space. It's not a lot of space, but I don't want to waste anything anyways. I already had this. So y'all don't have a software directory in your home, but I do. And so if I want to call any of these scripts, this is where we're going to get a little confusing. I'm in this directory called test. And the scripts that I've downloaded, they're in software Bio435. Again, this is just for me. This isn't for you. If you download it straight to home, that's fair. It's just if you do that, recognize to access these files, you would just call your home and then Bio435. But anyways, like whenever we've called maft, this program is globally available to everybody on this server. Right? Anybody who wants it can use it. And our Linux, our home directories are kind of set up to look for programs that are built in. And whenever I say it's built in, it's probably in like a specific directory called user bin or user local bin or something along those lines. These programs, maft is going to, I think, is in user local bin. Yeah, so maft is in this directory user local bin, and my Linux home knows to look for programs in user local bin. But whenever I've downloaded this Git repository, those programs, those scripts are not globally available. They're only accessible if you call them from their home. And so for me, its home is software bio 435. So if I want to call a script, if I want to call translate, I have to call it from its home. And so that's, again, software bio 435 and translate.py. Recognize I'm tabbing because I don't like to write stuff out. I rarely type more than 3 letters without tabbing. Rarely do I type more than 4 letters at a time. Translate.py. And so I don't have a help menu on any of this, so if you run it, it's just going to try to run something and then probably eventually fail. And so how we would translate, so we have this PW file, right? I have this FASTA file, it's DNA, it's a coding sequence, I can translate this. And so if I want to translate this using my translate script, it's going to be software about 435, translate, and then the file name. For me, that's PW test. Okay, and so by default, it's just going to print that stuff to the screen. It's just going to print the translation, right? The amino acid translation to the screen. We've seen this before. And so if I want to save it to the file, of course, I have to use my OpenCare to save that output to a new file. So that I may call this pw.aa.fast. So I know that it's an amino acid FASTA. Okay, so I'm going to less this real quick. All right, so we can see that this is an amino acid. There's our start codon, there's our stop codon, or stops, yeah. Why? There we go. Okay. All right, so all of them got translated. And again, to reiterate, whenever we make a codon alignment, all we're doing is we're translating to amino acid, we're going to align the amino acid, and then basically use that as a scaffolding for our DNA, right? So that our codons will match the amino acids, or at least the position of a codon will match the amino acid. So again, I'm going to use MAF to do this. And so MAF is nice because it's really fast, and it makes short, really good alignments, at least I think. And so I can call, so MAF does have a help menu, and it is pretty easy to read. So right, just the default state is mapped in out, and so the in is going to be an input file, and the out's going to be an output file. Pick your favorite name. A lot of parameters are mapped that we can manipulate, but we're really not going to touch. The only thing that we want to recognize about mapped is that we have this -- thread option. And so this -- thread option allows us to control the number of processors that we can use to run this program. And so this is the benefit of working on big servers. Nope. And so I think this server, our server, has like, I think it's close to 60 processors. I kind of forget the exact amount, but I think we have 60 processors to play with. That definitely doesn't mean we should use 60 processors anytime we run a program. It just means that a lot of people can use this server at once, and a lot of data can be processed all at once. That's the advantage of processors. They can make things go faster, and we can do more. And so let me map this real quick. And so I'm going to call my thread. Make sure it's thread. Yeah, thread. And I'm going to choose 4 processors on this one. It's a short alignment. It won't take that long anyways. But mapped, anyways, anytime we use mapped, we really don't max out more than 8 processors. I don't think it can use more than 8 processors, to be honest. Beyond that, we're just wasting resources. And then I'm going to call my in-out. In this case, it's going to be my PW align, the amino acid file, because right, I'm aligning the amino acids. And I'm going to save this as an amino acid align file. Right, so I know that this is amino acid and it's also been aligned. Okay, and right, took no time at all. It's done. Way better than print, way faster than print. And so now I have my amino acid alignment file. So I'll just look at that real quick. Okay, now it's gapped, and as any good alignment should be. I lost my stop codon, right? So I have this asterisk. Every protein ends with an asterisk to denote that that was a stop codon there. But I lost it because math really doesn't like non-characters. Like it doesn't like special characters like asterisks and question marks. But sometimes those will be present in a mathed in an amino acid sequence. Because a question mark might be like the sequence is gapped, or the sequence, part of the sequence is unknown. So it's just going to be a string of ends, right? Instead of seeing MESRR, if this is unknown, we know something is there, but we don't know the exact bases, it will be end out. So all of these will be ends. And an N does not reflect an amino acid. Sometimes there will even be question marks, right? We'll just have this long string of question marks. And so that can get a little screwy with the next step. It shouldn't right now, but it can later. So if I want to include those in math, if I want to include those special characters, I may have to also call the option any symbol. And unfortunately, any symbol is not written into the default help menu, but it is written into the like a web page manual. It got complained. It complained. Why did it complain? Any still. Oh crap. I even just ran this earlier today to make sure that I wasn't doing something stupid, and here we are. Is there any symbol? Am I misspelling this? Oh, I know. Because I know. Yeah, I know. I'm not going to worry about it. There we go. And it's done. Come on. And so those asterisks should be in place now. Yeah, now we have asterisks that denote we had a stop codon there. And again, if there is question marks, I don't think I have any question marks in here. Nope, I don't. But sometimes I will. Sometimes a predicted sequence won't be all that great, and there can be question marks in a translation. And that can throw off my next script. Right, because now we have an amino acid alignment, and we need to get back to that to a codon alignment. And so I have another script that's reverse translate. And let me see how I use my reverse translate, because I kind of forgot. I'm going to call reverse translate, and then the protein alignment first, and then the raw DNA sequences second, and that should give me a codon alignment. Yeah. Right, when in doubt, always check the help menu. If we forget how to do something or something's not running right, always check the help menu. So, software bio reverse translate. My amino acid, so that's PW, ALN, and then my DNA. So my DNA is my PW.fast, my PW test. That's the raw DNA sequence. And again, I'm going to make sure I know what this file is by naming it pretty well. I'm going to use cdn for codon.aln.fast. So I know this is a codon alignment. So if I list this, now I have my codon alignment. I should have gaps of multiples of 3. I should still have my stop codon in place. Yep. So this looks as good as I can make it with MAFT. Again, MAFT doesn't do this natively, but you can figure out how to make these tools work for you. It's a little silly. A codon alignment is not built into a lot of these programs, but nonetheless, we can make it. Okay. And so now we have a codon alignment. And so, like, where are we at? 20 minutes in? So we've learned Git, how to get stuff from Git, how to call stuff from that downloaded directory, and how to make a codon alignment on a server using a tool that doesn't necessarily make codon alignments. Handy, but nonetheless it's handy. All right, so if we're reiterating this stuff in Linux, or like stuff we've done in Mega, doing it in Linux, a little more tricky, but nonetheless we can do the same stuff. And not only can we do the same stuff, we can do the same stuff with better. So we can use better tools, right? We're not constrained to just muscle or cluster out. We can use a better aligner. We can use a better phylogenetics tool. And when we get really clever, we can do this all much, much faster and with less work than using it in Mega, than doing this stuff in Mega. And so the last kind of thing I'll mention, I'm going to provide a link in this comment. And so this is a quick manual for a tool called Aic Tree. And so phylogenetics is I would still say it's kind of a solved problem, but mostly not a solved problem. And so a lot of people keep developing new tools to improve like a maximum likelihood or phylogenetic software. And so Aic Tree might be the best tool that I have used for quick phylogenetics. Aic Tree is awesome, and it's awesome because it's easy to use. Because like previously doing an ML tree on the command line is a pain, and it still can be a pain. My previous software was RaxML, and RaxML's solid. It's just the commands to use it, it's not user friendly. And so Aic Tree, it's not necessarily, I don't know if it's an improvement on the maximum likelihood algorithm or search algorithm or anything like that, but where Aic Tree improves at is speed and usability. It's very fast and it's very user friendly. And so Aic Tree should already be built in. That should be something I have installed. And so it should be Aic Tree 2. And Aic Tree 2, right, it's just a phylogenetic software. It's going to use a maximum likelihood approach. Right, so it's just going to search tree space as fast as it can and produce the best tree that it can find. And so the help menu itself, let's see, let's try help, is long. It's really, really long. And this manual isn't necessarily super friendly because it's super long. However, the tutorial is really awesome. Theme among developers and bioinformaticians is to create a very long, cumbersome, and hard to read user manual. RaxML is definitely one of those tools that's not exactly easy to pick up. But if you scroll through this IQ tree document, it's very, very polite. And even just using this software is great. Another advantage of IQ tree is that we can make it find and use the best substitution matrix or substitution can't think of the word matrix, for lack of a better word, right? A substitution model, right? So GTR, JTT, right? These are K2P. Those are substitution models, and some models work better given with different data. And so the nice thing about IQ tree is that it will select the best model for you. It will do a model test on like 200 plus models and use the best one it found. That's awesome, because RaxML doesn't do that for you. It's either guessing or using a third party to find that model for you. But IQ tree will just do it for you. So IQ tree 2. And using this, I'm not looking at the manual itself, but I know that my -S is going to be the option that lets me bring in an alignment. Specifically, I'm going to use a codon alignment. So Peewee codon alignment. And quite honestly, that's all you have to do. That's the bare minimum to make IQ tree run. Awesome. Because RaxML, to make RaxML run takes like eight parameters, 8 commands to get this thing going. But with IQ tree, it's 1, and it's already fast. However, I can make it faster because IQ tree also lets me put in a number of threads. So I can call multiple processors to make this search go faster, right? Instead of testing one tree, be like, how good is this tree? That's okay. Build another. I can build multiple simultaneously and test them all together. And I think that is just a T, a dash T. Not a dash T, I think a capital T. Yeah, capital T will give you the number of threads that we want to use. So, capital T, I'm going to select 4. This is a small file. It won't take that long. If it were bigger, I might use 12 or 20. I don't know. And so now it's doing its model test, right? So GTR is a model. And so it's testing all of these different models. And it's done. Amazing. Amazing. Right, so it tested all of these manuals, right? So JC is one of the last ones texted. That's the Jukes Contour, but it's also one of the most simplest and less realistic. It starts out with GTR because usually those are pretty realistic models. We don't care so much about the plus F, plus I, plus G, etc. Not too worried about that yet. It's just variations of the GTR model. Not worried about it. But if you've taken at least some high level of stats, you may see this AIC or AICC or BIC. And these are like metrics of how good a model fit. Like given this alignment, given our nucleotide diversity, or nucleotide frequencies, given transition, transversions, etc., how good does each of these models fit that data? And we can do that with this AIC metric. And so the best model, whenever we test multiple models that are all kind of nested, all kind of related, we can get this AIC value. And so the best model is going to be the one with the smallest AIC. In this case, I think it will already tell me that the best model is SYN plus R3. And if we look at that SYN plus R3, there it is. This is going to be the smallest AIC value. And so under this condition, this was the best model selected. But we don't have to do anything like that. IQ tree already chose it. So at least under AIC, we got the same model, but under a Bayesian, this BIC, it's going to be this TIM model. Don't know what the metrics, what the parameters of that model are. Don't care. But that was what was selected. anyways, and then it built the tree. Didn't take very long. And it gives us all of these output files, right? It gives us 4 different output files. It gives us a log file, which is pretty much everything that was printed to the screen. Also got saved into this log file. Likelihood distances we don't want to care about. The IQ tree report can be helpful. So we can look at some of this stuff. Let's see what IQ tree looks like. Yeah, no, yeah, there's a model selection. And we also get our tree, right? So it does produce a graphical representation of our tree using dashes and these very simple characters. An IQ tree won't make a rooted tree by default. So this would be an unrooted tree by default. So we could eventually root it. It also gives us this Newick format. And we've talked about a Newick once. But it's just a graphical way, or it's a text way to denote relationships. Let's see a good example. Yeah. So anything that's like comma delimited are going to be closely related to each other. So if we see, I don't want to do this. I can make a better one. So like if I see 1, 2, 3, if I see, that will be a Newick format. And this Newick format in this example, it's saying that 1 and 2 are sister, and 3 would be ancestral, or it would be an outgroup. It's just 1 and 2 are more closely related to each other than 3 is, right? This is just a text way to show a phylogenetic tree. But our tree gets saved into a tree file. We don't care about anything that's gzipped. We don't want those files. They're gzipped because they're massive. The main file that we care about from this output is going to be the tree file, .tree file. So that's just going to be a Newick file, right? That's all it is this Newick file that's going to reflect relationships. And so if we want to visualize that, we can use our FileZilla, bring it back over to our desktop, and then open it up in Mega or some other program that lets us manipulate Newicks, right? So I'm not going to do any more than that. I think we've already kind of done a lot with Git, using scripts in Git to make a codon alignment, and then using IQ tree to build a tree. We'll probably get a little more complex with IQ tree in the future. Just setting a couple of options that test our tree. So like we can still do a bootstrap or something similar to a bootstrap with IQ tree. So I may save that. I'll save that for probably next time. And then a couple other things after that. But I'm going to call it there. And again, I would definitely encourage you to practice downloading using Git and using those tools with the file that you already have at hand, right? That you're allowed to play with. So until Wednesday, I'll see y'all later.